Right, ladies and gents, let's get locked in with some C2 bonding and how it all links into what I think is a very difficult concept to get your head around, which is electrolysis. So here's a very dodgy periodic table that seems to be as old as the periodic table, but it's the only one I can find. So what I'm going to talk about first is ionic bonding. So let's say that we have calcium, chlorine. So I'm going to add those two together. You can't see the numbers, but I'm just going to write the numbers in. Let's have a nice blue pen. Write the numbers in down here. So we've got a mass number of 40, and we've got an atomic number of 20. That's our calcium. Now for our chlorine, we've got a 35.5. And we've got a 17. Now that 0.5 is a whole different story. That's the mean average of the isotope, but let's not bother with that. Right. So this is the periodic table. Everything in this periodic table has neutral charge. It's like a fictitious table because in reality, the things in here, when they're out there in the real world, they want to react. And how do they react? Well, they react. Their reactivity comes down to the thing called electrons. So what I'm going to do is just draw myself a little calcium atom. So what I do is I look at the bottom number. Every periodic table has a key. So just look at the key. It tells you atomic proton number. It's got 20. Therefore, it's got 2 in the first shell, 8 in the next, 8 in the next, and 2 in the outer. But if you were feeling lazy, you could just look there and then just look there. And that 2 symbolizes it's got 2 electrons in the outer shell. I'm going to do these as crosses. I'm going to jump over to our friend chlorine. And it's got 17. So in its first shell, it'll have 2. In the second shell, it'll have 8. 2 and 8, and my math is 10. And the difference between 10 and 17 is 7. So what I'm going to do here is go 1, 2, 3, 4, 5, 6, and 7. So there we go. We've got calcium, we've got chlorine. There they are in the periodic table. But what happens in real life is when they're out there hanging around the atoms, they react. And what is it that happens when they react? So with our chlorine, it wants to fill its outer shell. They both do inevitably, but what calcium wants to do is to lose because it's got 2. It can either gain 6 or lose 2. There's less energy in losing 2, and it always wants to be energy efficient. So one of these little bad boys, these are electrons, that goes and sits there. And so what happens now? Chlorine is somewhat happy because it has a full outer shell. So chlorine gained an electron. It had 17 protons, it had 17 electrons. It's now gained 1, so that now becomes 18. So overall, it has a negative charge. If we go to our friend calcium, the thing is, we've lost 1, but it's still unhappy because it's still got another 1. So what has to happen is we need to get ourselves, ladies and gents, another chlorine atom. Here she is. 1, 2, 3, 4, 5, 6, and 7. So now that electron goes over here and sits there. Now this finishes the first part of the story because now what we get is we get our calcium atom that's not an atom anymore because it's lost 2 electrons. It had 20 protons. It had 20 electrons, but it lost 2 of those to 18. Difference between 20 and 18 is 2. And so it is 2 plus. Calcium is 2 plus. Chlorine is negative, but it's only negative 1 because it only accepts 1. But there are 2 of them. So the formula would be Ca 2 plus, Cl minus, but there are 2 of them. That's called the ionic formula. And the charge balances each other out. So inevitably, when it's bonded together, it's simply CaCl, calcium chloride. That's ionic bonding. That's higher level. Now we can take this to the next part of the story, which is electrolysis. No, let's just go back. So what does that actually look like? Well, we're talking billions and billions of these atoms. So A diagram that you'll need to be aware of is this one. Now this is your ionic lattice. So these are your calcium and your chlorine ions. And what happens is there's a force between them. This is called an electrostatic force because it's the opposing charges that attract one another. These are giant compounds, in Spanish gigante, so we're talking billions of them. Because there's billions of them, the forces are strong between the electrostatic force. Therefore, all of these, or one of the properties of giant ionic structures is that you require a lot of energy in order to break this electrostatic force. And obviously that's in the form of a solid. In order to make it a liquid, that's its melting point, you would have to apply a lot of energy, which is why giant ionic lattices have high melting and high boiling points. Okay, there she is. There she is. That's the one we're talking about. That's our calcium chloride. Now let's just say you deal with calcium and you sell calcium. So what you need to do is you want the blue calcium ions to be turned back to calcium atoms, and you want it separated from the chlorine. And so what you would do is you would place your ionic giant structure, which is calcium chloride, into what's known as an electrolyte. This is a molten state, so dissolved in water, or it's a high temperature in order to dissolve. And what happens is when it puts it in there, it breaks the electrostatic force. So now your ions, calcium ions and your chlorine ions, are free to move. So they're just moving around in there. And what we now need to do is introduce the next part of our puzzle. So this is our electrodes. This is our cell. We turn it on, we place it into the electrolyte, and because of opposing charges, the positive calcium ion will move to the negative electrode. And there's something here we need to remember, which is panic. That is positive anode. Negative is called the cathode. So this is where the higher level gets a bit more tricky. So we've got Ca2 plus. And what we want to do is turn it back into simply calcium, because it's obviously, it lost 2 electrons. So what we have to do is we have to add 2 electrons, and they come from the cathode, turning the ion into an atom, calcium atom. These are known as ionic half equations, and you will have to balance them. Notice that because it's Ca2 plus, it lost 2 electrons all the way back in this story. What we do is put them back on, and that happens up there on the cathode. The other thing that we have to introduce here is something called oil rig, another acronym. Now this means oxidation is the loss and reduction is gain. So as you can see here, the calcium is gaining electrons, so it is being reduced. Strange concept. Okay, let's just have a look. Oxidation is loss, reduction is gain. And because it is, you're adding 2 electrons to calcium, it's gaining 2, the gain is reduced. So it's being reduced. Similarly, when the negative chloride ions arrive at the anode, remember these are Cl minus. There's 2 of them. And so what would have to happen is you would have to take away 2 electrons to get two chlorine atoms. Let's go back. Oxidation is loss. The chloride ions are losing to, they're taking them away, so it's becoming oxidized. So that is what links, and then you can take your calcium away and do whatever you want with it, build a bike, make a car, whatever. But that's how you separate metals that are very, very reactive by the process of electrolysis. Lots of big words, two acronyms, and then these ionic half equations that are also rather challenging. There is another one, so let me just quickly bring up my 1862 periodic table, and this one is aluminium oxide. This is known as bauxite. That's its mineral name as it's found in the ground, in a rock. So let me just write down the little numbers. We've got aluminium 27 and 13, and we've got oxygen 8 and 16. So what we have to do is bond these together. This is the shadow. There we go. So all I have to draw is the outer shell. So here's my aluminium. It's got 13, so that means it's got 2 in the first shell, 8 in the second, and I'll do these as crosses. It's got 3 in the outer shell. Oxygen, group 6, so we've got 2 in the first, and then 6. 1, 2, 3, 4, 5, and 6. It needs 2. So this one sits there, and that one sits there. So that, in theory, obviously they don't have feelings, but happy. And so oxygen becomes 2 minus because it gained 2 electrons. It was 8 protons, it was 8 electrons, but now it's gone to 10. And hence the 2 minus. But we're still not going on over here. Aluminium's still upset because it's still got another one. So we have to introduce another oxygen. 1, 2, 3, 4, 5, and 6. So that one goes over there. So this one can turn its frown upside down, but we're still not there because this one still needs another electron. So we introduce another aluminium. And 1, 2, and 3. So that one can now go there. And we've got 2 left. And so the final piece of the puzzle, I know this is quite challenging. 1, 2, 3, 4, 5, and 6. And that goes there, and that goes there. So overall, the ionic formula for aluminium oxide is Al. There's 2 of them. There's 1, there's 2, and each of them lost 3 electrons. And so they are positive 3. Compared to the oxygens, which we have 1, 2, and 3, but they gained 2 each. So that is the formula for aluminium oxide, found in the ground as bauxite. Same process occurs with electrolysis. It's an ionic giant lattice. You put it in the electrolyte. That's called cryolite. And the ions separate, charge moves, and there we go.